Our planet's climate is changing. The ice caps are melting. Sea levels are rising. Weather patterns are getting more extreme. Is human activity contributing to this change? And if we are responsible, what can we do? We need to consider our actions as nations and as individuals. But what are we going to base our decisions on? We need to be sure that the choices we make are the right ones for the planet. And the way to do that is science.
From the evidence I've seen, I think something's happening to the climate. Most people agree that the climate is getting warmer, but the question is it due to man-made changes? That's one of the reasons why I like the work I do, because we're trying to get the data to understand climate change. But personally, I think climate change is happening, and I think we do need to do something about it. And the sooner we start doing something about it, the more impact it will make.
So what is the situation? The more observations we can make, the more we will know. And with enough effort, we can build up the big picture of what's happening to planet Earth.
I think it's not one single body of evidence, but it's the collection of evidence that leads us to believe that climate change is definitely happening. The only tool really available to us is to get current data, take that for as long as possible, and then extrapolate it into the future. But even that isn't a surefire way, and if it was, everybody would be making lots of money on the stock exchange.
There are thousands of scientists from all areas of research contributing to our knowledge of the planet. They're doing experiments, amassing data, and creating theories about the Earth's climate. They want to try to explain what is happening and predict what the future holds. Dr. Maggie Adarin is just one of the people involved. Maggie originally trained as an astronomer looking out into space. But her expertise as an instrument maker and stargazer has given her the skills needed to join the worldwide effort to understand global warming. And her journey to becoming a rocket scientist started as a small girl.
I got really interested in space at a really young age, at about 6. I think there's a number of reasons for that. Firstly, there was the space race, people launching off, landing on the moon. And to me, that was so exciting. Also, I saw a beautiful book on astronomy when I was quite young. And sort of looking at that and looking at the images, I thought, yes, I want to find out more. And so from that, I made my own telescope when I was about 15. And after building this, it gave me access to space in ways I'd never had before. I could see the craters of the moon, and it was beautiful. But also it got me interested in instrumentation, because this is something I'd made with my own hands, and suddenly I was able to see, the universe with it. So I thought, how can I work this into a career?
From that beginning, Maggie set her sights on physics. A PhD at Imperial College London led to Ministry of Defence work on a missile defence system for fighter planes, and then a landmine detector that used ground-penetrating radar. But Maggie's first love, astronomy, still had a pull. And in 2003, Maggie found herself working on an instrument for a telescope in Chile. There's no doubting that Maggie has a real passion for the stars.
I always see telescope as a light-gathering bucket, and the bigger the bucket, the more light you gather. The really exciting developments in more recent years is extrasolar planets, planets revolving around other stars.
And that light-gathering power has helped shape our view of the universe.
We live in a galaxy called the Milky Way, and it's estimated that there are 125 billion stars just in our galaxy. Hold that thought. If you think of each one of those stars as a sun just like our own, with a number of planets going around it, how many planets are there just in our galaxy? And with space instrumentation and bigger telescopes, we've been looking further and deeper into the universe. And from this information, we've been trying to estimate sort of the number of galaxies in the whole universe. 100 billion galaxies. That also leads on to other questions like, is there life out there? And I think I and many scientists do believe that there's life on other planets, because there are so many planets in the whole universe, it seems quite likely.
But for Maggie's next project, she's not building instruments to look out into space. She's turned her gaze to look back down at the Earth. Today, Maggie's on her way to Astrium, a European space company with labs in Hertfordshire. Here, in their specially designed workshops, satellites are put together under dust-free conditions to protect them from contamination. One such satellite will carry an instrument designed by Maggie and her team into space.
I've been working on an instrument called Aladdin, which is part of a satellite called Aeolus. Now, Aeolus was the Greek keeper of the winds, and so that's why the satellite is named after this. And that's exactly what Aeolus wants to do. It wants to look down through the Earth's atmosphere and measure wind speeds. And this will give us a better understanding of climate change and also give us better weather prediction.
So how will Maggie's wind measuring tell us about global warming? By following wind patterns over a number of years, scientists will be able to see if they're changing. Changing wind patterns can give us an idea about how global weather patterns are changing. These changes can then be compared with other climate patterns and will add up to a bigger, more complete picture. Of course, this kind of complex technology didn't just come from nowhere. As with all Maggie's instrument building, it's based on the work of hundreds of thousands of scientists who've contributed to our knowledge. In fact, Maggie's instrument making has origins that can be traced as far back as the early 17th century.
Galileo was the first person to point his telescope up at the sky and then record the results. And that makes all the difference, because the fact that he recorded it means that it's there for prosperity and people can understand what he did. And eventually people worked out that the Earth is actually going round the sun, and why we see it sort of going up in the sky is because we're actually rotating round and we're spinning on an axis. So that gave us better understanding again.
Galileo's discoveries were literally world-changing. Perhaps not surprisingly, the next leap forward didn't come until Sir Isaac Newton invented a different kind of telescope.
Newton was the first person to come up with a reflecting telescope. And what he did is he sort of fashioned a mirror and then used that as the magnification power. And he got a shape called a parabola. And that has the ability of taking light, which is coming from very far away, and bringing it to a nice, clean, sharp focus. So reflecting mirrors were the way most larger telescopes went, and they got bigger and bigger, because you do want a fairly large telescope, because the bigger your telescope, the more light you can gather.
As telescopes got bigger and bigger, we found out more and more about our universe, until we hit a major barrier.
When you get your telescope to, let's say, about 4 meters, there are atmospheric turbulences, so disturbances in the atmosphere, and that's what makes stars twinkle, which is brilliant and very romantic to see. But for astronomers, it's a real pain, because you want a nice steady image of your starlight coming through. So the technology needed to be developed again, and the next thing that was brought in was adaptive optics. With adaptive optics, it actually monitors the atmosphere, and it looks at the turbulence, and then it puts some corrective factors into one of the mirrors to take out the turbulence. So rather than your stars twinkling, you get a nice firm image, which is just what the astronomers are after.
Having overcome the atmosphere hurdle, the sky was literally the limit. Maggie and others were building instruments that could see back in time to the very beginnings of our universe.
One of the other things they did is, because of the limits of ground-based astronomy with ground-based telescopes and the atmospheric turbulence, they put some telescopes up in the sky, or beyond the sky, in space. For instance, Hubble has been able to take some amazing images.
And this time it's Maggie's work that has to survive the rigours of takeoff to get into space.
As it approaches the pressurized mating adapter on the leading edge of the U.S. laboratory
Because it's quite a step forward in the technology, you want to take it in small stages. And we built a version of the Aladdin instrument that was actually flown in an aircraft. So rather than launching it straight into space, which is quite high risk, you do some what they call risk mitigation, and you'd actually use an instrument like that, maybe just sort of on a tower at first, and then maybe up in an aircraft before you actually design the whole thing to go up into space. What I've got here is the front end unit, and this consists of a detector and a lens in the front, and it gathers light. But the whole Aladdin instrument works by passing a UV laser down into the Earth's atmosphere. And as that laser light passes through the atmosphere, the laser gets scattered off particles in the atmosphere. Now, if you think about it, particles are very small, so the amount of light that they sort of scatter is very small. So the detector actually sitting inside here, its detector would be quite familiar with, because it's the sort of thing we find in our digital cameras. But of course, this is space science, and so it's a lot more sophisticated and a lot more expensive. The job of this unit, it takes the light, it takes the actual packets of light, the photons, converts them into electricity, and then converts that into a signal that can be beamed down to Earth. And we picked up by receivers, processed, and then presented in maybe in terms of an Excel spreadsheet or in terms of an image, and that will be what's presented to the scientists.
The beauty of Maggie's instrument is that it provides its own light source, so it can work continually day and night. Orbiting the planet, Aeolus can look down on the Earth's winds and provide scientists with invaluable data.
What Aladdin will give us is it will give us much better global coverage. It's up in space looking down. It will give us better resolution of the different layers of the atmosphere, and it stays up there for a lot longer than an aircraft will. And so it will continue giving us that global coverage through time, so we can see the evolution of the wind speeds in the atmosphere.
And with Aeolus beaming vast amounts of data back to Earth, a whole raft of scientists will be required to interpret the information.
Processing the data is one thing, but interpreting the data is quite another. And that's where scientific know-how comes in, looking at the data and trying to understand it. You can generate images of 3D profiles showing how the wind is sort of moving through the atmosphere across the globe, and the development of maybe things like hurricanes. Because it's a European Space Agency satellite, it will be aimed at sort of European scientists, but that will be published in papers and then go through the peer review process and then circulated to people across the world.
Turning the raw data into computer models of the wind serves several purposes. Firstly, the scientists can compare their models and use these to see how wind patterns have changed over time, and then predict how things will change in the future. Secondly, the computer-generated images will be more effective in explaining what's happening to non-scientists. Climate change is a hot topic for politicians and the general public alike. People will find it much easier to understand these images than if they were just given the raw data.
We're looking at the variables of climate change, so each of the parameters that contribute towards climate change. And wind speed is just one of those parameters. And through ESA's Living Planet programme, there are a number of other parameters that are measured and understood. And so they all feed together to give us a top-level view of you change this, and that results in this. Unfortunately, it's very hard to get agreement on things like that. It's like doing things by committee. You might get a consensus, so the majority will agree, but some people will see the data in a slightly different light, or maybe process it in a slightly different way, and so draw another conclusion. But that's what science is about. You take the data, it's processed by a number of different people, and then you come together and see if you agree on the principles. And sometimes there's disagreement, but we try and find consensus. And sometimes it's a little ambiguous, in which case you go and try and take more data to narrow or better home our understandings, really.
And whatever data does come from Aeolus, it must be seen as just part of the overall picture, with many other pieces of scientific research supporting or contradicting it. The winds of change may be blowing, but are they for good or for bad?
From a global perspective, climate change is quite a quagmire. It's quite complicated because different people want different things. The fear is if no one does anything, it just goes on, and the problem just gets worse and worse. The sooner we do things, the more effect they'll have. So I think some consensus does need to be brought to bear, but I think it will be the people of the world that influence their politicians to do something. If we make it important enough, then something will happen.